Okay, dears, welcome back. And you have started watching lectures on support vector machine. Today, we are going to introduce you with a very important concept of formulating dual problem in support vector machine. Why it is required at all and how to solve, everything we'll discuss right from the beginning. But before that, just quickly recap what you have studied so far. You have studied, by the way, I saw in my earlier lectures that sometimes I forgot to give this notation, vector notation with W. W is always a vector. So please consider this sign. Sometimes it is not needed if you can remember that this is a vector, support vector is a vector. So everything actually, and alpha is a Lagrangian multiplier, all kind of things. Okay, our basic objective was to maximize the width of the gutter. Okay, and we formulated a problem because fundamentally from geometry our objective was to maximize this. This is the width of the gutter, right? But for mathematical convenience, we form a dual function. Now I am introducing slowly that concept of dual. Dual means maximizing this means minimizing 1 by this. Okay, that means we got this. Okay, and then further for mathematical convenience to make it that function to be a quadratic, we just did this. Okay, but this is maximization problem. Then we the dual of this maximization problem is minimization problem. Okay, and this kind of mathematical convenience duality you have seen all along our lectures on machine learning. Another example I can give you in linear regression. LW was, if you remember, the maximum likelihood estimate, right? LW was actually some constant minus half sigma. So that is a statistical interpretation of linear regression problem, which we have studied in our lecture. Okay, so we are trying to maximize this likelihood function LW, which turns out to be some constant minus, I am not writing exact detail, minus this. Since this is minus, maximizing these functions, dual to it is actually minimizing this, and from there we got the cost function, if you remember. So these are sample, these are the levels of the sample, that is if it is housing cost, so these are the features. Okay, the floor area, this floor area, number of room, and this is the cost of the house. And it turns out to be that this cost function you got from maximum likelihood estimate, and maximum likelihood estimate of parameter W turns out to be minimizing this expression, that is the objective function, because minus sign is here. So this is, so maximizing this is equivalent to minimizing this. So this problem, minimizing this, is dual to maximizing of this. So, okay, so this is the actually very simple concept, but simple concept is not so simple when it is not only having a function but a problem where you have an objective function and you have constraint. So constraint actually make this thing a little bit difficult, and we will study those things in detail. But before that, you know that my objective function, that is my object, this is a Lagrangian function L, which we formulated. We are solving this. By the way, some concept of optimization will be required to understand the simple things, especially quadratic optimization theory, little bit. And but I also told right from the basic that how it works. Okay, first you have an objective function, you create a Lagrangian function incorporating objective function as well as the constraint. Constraint you are multiplied with alpha, that is a Lagrangian multiplier. Okay, and then you are trying to use calculus method for optimizing it. Here it turns out that the minimization of this, since minus sign is there, is the maximization of the dot product. So if you can again just see that this is the garter. Okay, say these are my ith support vector, and by the way, support vectors are those vectors which are at the boundary of this class. These are the support vector belonging to this class, and these are the support vectors. These are the support vectors belonging to the -1 class. Okay, they are at the boundary. Why they call support vector machine? Because they are supporting that structure, that is the classifier here. Okay, and in the middle of the garter, my classifier is formulated. So that you know. Okay, so that means everything remains same, because this is the Lagrangian multiplier. Once it is figured out, this is constant, this is the level, the data is given to you, so levels you know, and it turns out to be that dot product minimizing means maximizing the dot product between. So this is extremely simple computation. So if you consider that this is ith dot product, ith support vector Si, then you just try to figure out, make the dot product between I and j equals to 1, 2, 3, 4, as many. Okay, and whatever will be maximum value, you put it here, and that's the that will minimize L. Isn't it great and very simple? So this is the byproduct which you have got from the primal problem, and what we have seen that I also try to explain how it works with a simple example which you have understood, I believe. So now I will try to write for your convenience again. Once you have formulated the problem, say our primal problem was support vector machine, right? SVM, formulation of dual problem. Okay, so our primal problem was minimize over W half W squared. Okay, now subject to constraint. Okay, these are support vector plus B minus 1 greater than equal to 0. Okay, so this was our actually primal problem. This is the subject to this is the constraint, and actually if you try to have an insight that what constraint is doing, what is the role of constraint, then I can tell you okay, what it is doing. Say I have, so this function is my quadratic function. Okay, so I have a contour. Okay, quadratic function is convex in nature, so I can represent that function, okay, in the form of contour. And then these are my constraint. This is a straight line equation of a straight line. So what it is doing, greater than something, say this is, and for each support vector you will have one constant equation, right? Support vector 1, support vector 2, support vector 3, as many support vectors are there, that many constraint will be there. Constraint is actually trying to eliminate that. It is constraining this search space. So as many constants are there, so now it will eliminate this. If the constraint is here, so it will eliminate that space. Okay, so as many constants are there, your search space will be, that's why they are called constraint. It's very good, right? And you don't have to search all these things again and again. So remaining, because your solution lies in the remaining part. That is what the constraint is telling. Okay, so this is your intuitive understanding what this problem, primal problem means. Now, once we have solved the problem, okay, which we have already, and the solution I can just rewrite, okay, equals to alpha I minus half or I over j alpha I alpha sub j y half x I y sub x j. Then you had support vector I dot support vector j. Okay, so this was my solution, isn't it? Okay, and also we got W is actually equals to alpha sub I y sub x and si. Okay, so primal problem has given this, and it has given another thing, because if you just recapitulate or you can see the videos again, then you will see when we did this, making it to 0, we got this, and we because this is a function of W, B, alpha. Okay, so when we did this, we got one very important relation equal to 0. Okay, so what it is telling? It is telling that with all the levels, the summation of the so this is the Lagrangian multiplier, summation of all this will be 0. Okay, so these are the two byproduct which we had in our primal problem, and using this primal problem we have solved a problem. We could find the decision boundary. So that's it. Then we can design an algorithm, and then once the decision boundary is figured out, then you can use. So once the support vector machine is designed, then you can use it for prediction. Okay, so for prediction what you need, again, that is what we have already studied. Okay, this is our decision rule, the first lecture, okay, first or second lecture in support vector machine. So if this is greater than or equal to 0, then it will be the sample belongs to positive class. Then so by computing this less than 0, the sample belongs to negative class. Okay, so that's how you will use support vector machine. Okay, once you have figured out you have designed this. Okay, W is, once W is known, and very judiciously this is bias we have incorporated to simplify it here. Okay, and we got the value of B in my earlier example, and that is we normally follow in case of finding bias. So that's it. So primal problem is able to you are able to design the problem, you are able to predict also. Then what is the problem? Problem is, if you remember, we assumed that I have samples and these are my support vectors, and this is a toy hand calculation problem. That is fine, but normally nobody is going to tell us that this is my support vectors. These are my support vectors. They will not be known. If it is not known, then this formulation has limited ability to solve real world problem. In the real world, what will be given? You will be given the training set, right? That these are the sample belong to positive class, these are the sample belongs to the negative class. But out of those samples, who are support vectors? Normally, we will not know. Okay, so can we reformulate the wonderful idea of primal problem of support vector machine? And as I have told you that for mathematical convenience we do the dual. Okay, so that is a primal problem. This is what we have solved, is called LP primal, and that is the question we are asking. Can we really reformulate our primal problem into a dual problem, okay, and overcome this issue, okay. So that is the basics of dual, okay, formulating dual problem of support vector machine. Okay. Now, to solve this dual problem, I actually would like to tell you one story which will help you to understand the concept of duality. Okay. In many practical problems, we actually take the help of dual problem in solving those problems. Say a big software giant is trying to produce a design. So a software giant okay, wants to produce a design, say X, okay, say design X, and the cost associated with that design, say, is represented by f of x, okay, because developing any product, software, hardware, whatever it is, requires man, machine, other resources, electricity, building, all kind of thing. They are called resource. It requires resources, right? So it will have a cost, that is cost of design or cost of production, design or production, okay. So that is the cost, f of x. Now, normally in those big companies, the production cost is or process is such that the production cost is high. So what they do, they outsource, okay, outsource the design, okay, to another company, and say this is the company which is doing some analysis that I need to minimize. So what is the objective? If company wants to manufacture or design this product, minimize cost, right? And there should be some constraint, subject to constraint, subject to your some man, material, all kind of thing which will be required for design. Okay. Say I have, subject to some constraint, say a particular example I am taking, x1 plus 15 x2, okay, say minimize f of x, f of x equals to, say 20 x1 plus 15 x2. So x is actually x1 maybe resource office cost, x2 the labor or human resource. Okay, so this I need to minimize subject to some constraint, say x1 plus x2 less than 60. Say there could be number of constraints actually, 160, all kind of. This is office cost. So this is related, x1 is related with office cost, x2 related with labor cost, and suppose they are contributing to this constraint, and then say x1, x2 must be greater than or equal to 0. So these are called constraint. Now, with this, analyzing this constraint, that okay, they have so many people, so many office cost will be very high, people in big companies get more salary, so this will be high. So after analyzing this, they decide, no, we are not going to produce this, we are going to outsource this. Now at this point of time, say outsource company get this product, and then what is their objective? Their objective is to maximize profit, right? But maximizing profit means they will not, this outsource company will not give them any money which is which will be greater than the minimum amount which they would have manufactured or designed in their own company, right? So say f of x, if this is the optimum cost, so the challenge is the outsource company has to produce that product within this cost, okay? And they will have to then reformulate their objective, okay, objective function. Their objective is what? Okay, I will get this amount of money that I know from my outsourcing company, but still I will try to maximize within this minimum value. I will try to maximize that profit. So the outsourced company's objective will be maximize profit, okay? Maximize profit, say 60 y1 plus 160 y2. This is the maximize profit, okay? So this is say f of y, also this subject to constraint. They will also have constraint, right? That they will have to pay their salaries or their people, okay? And say, I am giving you a rough example to actually introduce you the concept of dual problem when it is a problem with constraint. When there is only a function, duality is very straightforward, okay? Minimization is replaced by maximization. But when you have constraint, then we'll have to satisfy, we'll have to formulate the problem in such a way. Seeing this, we'll have to see the I'll have to maximize profit, then my maximization function is actually constraint of the earlier function, lower bound, okay? So maximum is the lower bound of the earlier primal problem. This is if we call primal problem, and this is a dual problem, okay? And judiciously we'll have to formulate the constraint so that I can maximize my profit by designing the product or manufacturing the product within the cost f of x, which is minimum. So my problem is maximize minimum of this function, okay? Okay, so this is called dual. This problem is dual to this problem. If I call this primal problem, this is the dual problem. So one take home is you cannot whimsically design the dual problem, because actually these two problems, their objectives are same. So you cannot just formulating very judiciously. You have to formulate the constraint. You will have to judiciously formulate your objective function. and these constraints need to obey certain condition. So we are, without going detail with this story, I try to tell you that primal problem and dual problem, how they really exist, and in our case we'll just extend, having understood their existence, we'll just use convex optimization theory, and just concept-wise they are same, that we will formulate the dual problem for support vector machine. That we will discuss in the next class. But here I believe you have understood that primal problem and dual problems, their objectives are same, and they are very useful concept wherever there is a primal problem to design a dual problem, because the companies which the outsourced company which are getting money from the parent company, that is limited. They will not give the money which would have been more than if they would design or manufacture that product. So that's the biggest constraint, right? And accordingly they will have to maximize their profit by formulating seeing their constraint and manipulating with the constraint. And these are actually will be dancing with the help of, they will be following different process, they will be following, that is taking different Lagrangian multipliers here, okay. They will reformulate the process, some process what big companies would have followed, they will not follow, okay. So they have different constraint, okay. So that's the concept, that primal problem and dual problem, and we are going to discuss in the next class. Till then, stay safe and have a nice day. Bye bye.